Here. All right, welcome. It's Wednesday, March 1st. We're finally into March. No one likes the beginning of March, but everyone likes the end of March. So we're getting there. We're getting there. All right. So last day, we finished, let's see here, just for some review, right? We talked about equivalent payments. Equivalent payment streams, or I'll just say payments here, right? So where we have to move money around and use the future value function. Future value is P times 1 plus R times T, right? And we can solve for the future value, or we can solve for the principal amount. And we can solve for R and T, but it's a little more rare. And so usually we're just moving things around and making sure that we are repaying the same amount that we originally agreed to, right? And so, right, we can solve for future value, or P, and that timeline is going to be really, really helpful. Okay. We also solve for unknown payment amounts. Okay, so we also solved for unknown payments, unknown equivalent payments. Right, something where you have maybe something like this. You're going to make a payment, one payment 1 year from now, and another payment of the same amount 2 years from now, right? But we have to take into account that you'd have to pay more interest on the one from 2 years ago, or 2 years from now, than the one from 1 year from now. And so then we trace these back to some principal amounts, right? And maybe they have to add up to $5,000 or whatever the loan amount is. Usually it's a loan amount. Okay. And so this was the trick that we used, right? And we can even do things like 2x, right? If I want to make a double payment 2 years from now, right? Double the payment amount, then that's fine too, right? And so that's just a little example. We're not going to do one because they're quite lengthy. But we did do a thorough one last day. All right, so I did sneak into our notes from last day that section 4.7, it just talks about general strategies for solving these questions. And so I try to highlight that as we go, right? Pick out all the dates. So make a list of all the dates that you have, assort them so they're chronological, and then put them on the timeline. That's a good place to start. Then start putting the dollar amounts on there, and then start figuring out which way the money is moving, right? And so we've already kind of talked about that. So today, oops, helps if I have a pen handy. Okay, there, that looks weird. So I'm just going to start by 4.8, which is the last section in chapter 4, and then we're going to start chapter 5 today as well. So 4.8 is just kind of a cute section on changing interest rates. What if a bank has a changing interest rate, right? So for example, you get 2% to start, and then if you keep your money there for 6 months, they reward you by bumping it up to 2.5%, right? And then every 2 years or something, it increases by 0.5%, right? As a reward for keeping your money there, right? And so that can happen. And so it's not really, it is an example, but just to illustrate the idea, right? Say the interest rate, so say interest starts at 5%, okay, and increases, amazing interest rate, and increases by 1% every 4 months. Every 4 months. Okay. What's the value of $1,000 investment after 1 year then, right? So we'll be able to solve problems like this. So what is the value of a $1,000 investment after 1 year? We have the tools to solve this, but it gets kind of tedious depending on how many times the rate changes, okay? And so here, note, we already have the tools. We already have the tools to solve this, but it could get tedious. Right? So what would it look like? Okay. If I have a timeline and every 4 months, right? So it starts at 5% and then every 4 months it increases by 1%. Okay. And so here on my timeline, what's that going to look like? It's going to look like this, right? Here is 1 year from now. Here's today when I invest $1,000. Okay. And then for at the 4 month mark, 4 months, right? I have a rate of 0.05. Okay. What I can do is I can figure out the amount of interest up to this point, right? And so here, what I can do is I can find I1, right? The amount of interest. I'm not cashing out yet, right? And so I'm just going to find the amount of interest up to that point. Okay. So then I pick up here and I go to the 8 month mark. And we can find I2. So for 4 months, right, it was at a rate of 6%. And maybe I should make these a little bit brighter. Rate of 0.05. And here the rate of 0.06, right, increases by 1% every 4 months. So then 8 months to 12 months is going to be another interest rate, and we'll be able to find I3 here. And the rate for those last 4 months is 7%. Okay. So then the total value after 1 year is going to be P. So 1,000. So here I'll say P is equal to 1,000. That's your principal investment amount. Okay, so P plus the amount of interest for the first 4 months. So plus I1 plus the amount of interest for the next 4 months, I2, and then again, I3. Or, because remember, the future value formula is just P plus I, right? And so now I just have multiple I's, okay? Or, wait, why did it zoom in? Or we can use the formula. Finally, where's my formula sheet? It took us a while to get here, right? We spent a lot of time working with this formula here. The future value is P times 1 plus R times T. And now if you really dissect it, then you'll see that, okay, well, this is basically, it's the same formula, except I can have different interest rates. Okay. I'm going to copy this whole thing in. Or we can use this formula, that one there, right? Which allows for changing interest rates. Oops. Allows for changing interest rates. Good. So either way, right? And of course, there's a way we could derive from this formula here, right? And so this is the total value after 1 year is a future value, right? So you could replace that with just the future value is P plus I2 plus I1 plus I2 plus I3, right? Or how about we just use this formula right away, right? And then you can go back and you can try this one if you want, but I'm just going to use the formula. Okay. So the future value is P times 1 plus R1 T1 plus R2 T2 plus R3 T3. Okay. So let's put little subscripts on here, R1, R2, and R3. Let's also add, maybe blue, T1 is 4 months, right? So 4 over 12. T2 is also 4 months. My 2s look like 1s today. 4 over 12. And T3 is also 4 over 12. Okay. All right. So we want to find the future value. The principal amount invested is 1,000 times 1 plus the first rate was 0.05 for 4/12 of a year, right? T is always in years. That's going to be super important coming up later today. Okay, so just T is always in years, plus 0.06 times 4 over 12, right? Each chunk is 4 months, and so that's easy. Plus finally 0.07 times 4/12. Okay. Excuse me, little silent sneeze. My sneezes are usually silent. All right, so 1,000 times, so what I'm gonna do to simplify things a little bit is I'm gonna collect like terms, because 4 over 12, I've got that common multiple of 4 over 12. So 1 plus, and then let's see here, 0.05 plus 0.06 plus 0.07 is 0.18 times 4 over 12. You don't need to do this step, right? But just makes it a little bit cleaner to look at. Okay. I'm just checking my math here, 12, 13. Yeah, okay, good. And so the future value is 1,000 times 1.06. I'll just confirm here because I didn't check my my work before class. Let's see here, 0.18 times 4 divided by 12 is 0.06 plus 1.06. Okay, good, times 1,000. So the future value is $1,060 even. Okay. So what I want you to do just on your own, you can try solving this the other way. This by finding I1, I2, and I3 to confirm that you get the same answer. I think I remember I have a little, okay, another quick example. The Yeti with 2 T's, I don't know, has $20,000 to invest for 6 months. Wow. His bank pays 3.3% for the first 3 months and 3.5% thereafter. What amount will the Yeti have after 6 months? Okay, so it always helps to draw out a little timeline. In this case, it's relatively simple, right? And so there's not a lot that you need to jot down, but so you don't have to, but I think it helps. So he has $20,000 to invest today for 6 months. So here is the 6-month mark, and for 3 months, the rate is 3.3%. So the rate 1 is 0.033. Okay. And let's see, time 1 is 3 months over 12, so 3/12 of a year. And then I just show that it's just a slightly different rate. Rate 2 is 0.035. And it turns out 3 to 6 months is, again, just 3/12 of a year. So then I want to find this future value. All right, P is 20,000. All right. So the future value is P times 1 plus R1 T1 plus R2 T2. $20,000 times 1 plus 0.033 times 3/12 of a year plus 0.035 times 3/12 of a year. Let's see here. Can I do it? Okay. If you're careful with your brackets, you can just do it in one line, but you have to be really careful about your brackets. Times 1 plus, and I'm going to put these in brackets, 0.033 times 3/12. Close that bracket, plus 0.035 times 3/12. Oops. Helps if I divide 3/12. Close a bracket, close a bracket. You'll have $20,340. Hey, that's for 6 months. That's pretty good. Yep. Oops. How do I? 20,340. So what amount will the Yeti have after 6 months? Another thing that we haven't really looked at is, okay, a follow-up question could be, how much interest did he earn? How much did he earn in interest? You could use the I calculations, right, individually, or you can just remember that, okay, if I have the future value and I have the principal amount, right, then whatever the remainder is, that must be how much he earned in interest, right? And so therefore he earned, and I'm going to try to keep it on this page here, he earned 20,340 minus 20,000, which is $340 in interest. Yeah. Good. All right. Let's see here. You guys ready to start chapter 5? So chapter 5 is on compound interest. Versus chapter 4, which was on simple interest. Okay, so we've talked about simple interest and we learned a lot of skills around simple interest. What's really, really nice is that a lot of those ideas, right, also work in compound interest, okay? What compound interest is instead of, okay, you invest some amount and at the end, you get that interest plus the principal amount, right? What happens is with compound interest, at some compounding frequency, so let's say monthly, right? What happens is the interest is calculated up to that point, right? And then baked into the principal amount. So then your principal amount is increasing. I think of it as a snowball, right? It's increasing at each compounding, right? So monthly in this kind of fake example, right? And so what's really nice then is you're earning money on the interest that you've already earned, right? Instead of just, okay, well, you can only earn interest on your principal amount. Okay, so here, just to clarify, and I wanted this color. Simple interest. We earn interest on the principal amount only. We earn interest on the principal amount only. Compound interest is when we're going to be earning interest on the interest that we've already earned, as well as the principal amount. Okay, so we earn interest on the principal amount and interest earned up to that point. Okay, good. So just like before, right? And so we're going to have to change a couple of things, right? The interest rate, okay, it's going to change slightly. How we calculate time is going to change slightly. Everything else stays the same, okay? And so let's see here. Oh, 5.1. I almost started without labeling it. 5.1. is just the basics, which in today means just terminology, right? Just establishing some terminology. Okay, so compound interest is when the interest earned is calculated at some compounding frequency. Is when the amount of interest earned is calculated at some specified compounding frequency, or some specified, let's just say frequency. Okay. Which leads us to compounding frequency, which I want to define. Wait. So compounding frequency is denoted by F. Okay, and so the compounding frequency is how many times per year. It is the number, let's see here. The frequency that interest is compounded I'll put in brackets the number of times per year. We have some experience dealing with years, right? Right, we talked about, okay, there's 365 days in a year, there's 52 weeks in a year. And so I'll just review those in terms of the compounding frequency, but you know all of those already, okay? The compounding frequency is denoted by F. So it's denoted by a lowercase f. Okay. Okay. So I've got a table here that I want to make. Let's see how many 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. Let's see, how can I make some room here? Just gonna bump this up. There. Because I do want it on the same page. Okay. So denoted by F. Some common frequencies are annually. Okay. And so I'm just going to start from largest to smallest, right? And so annually, which is F equals 1. Okay. Semi-annually, so here, once a year, once per year. Semi-annually means twice per year, which means F is 2. Quarterly is 4 times per year, So F is 4. Oops. Oh, man. Monthly. 12 times per year. F is 12. Bi-weekly is 26 times per year. So F is 26. Weekly is 52 times per year. So F is 52. And then finally, daily. We don't really do less than that. 365 times per year. There's a special case where it's compounded continuously, but I'll save that for later. 365. Okay, so we need to have these memorized. You guys are working open book, right? And so definitely have these handy somewhere because we're going to need these frequencies. Okay? They're part of our calculations. Okay, so you'll need to memorize these. Must memorize. Right, or write them down in your case, right? But just in general, you should have these memorized. The ones that give people grief, or the only one really, is maybe the quarterly and the bi-weekly. Okay, 4 times per year, it's confusing because that's actually every 3 months, right? And so that's the only confusing part about quarterly, and then bi-weekly is 26 times per year. Okay. And so we need to know the frequency, F, in order to solve for the number of compoundings. Okay. So we need to know, the frequency, the compounding frequency in order to solve for the number of compoundings. In order to solve for the number of compoundings. Yeah. The number of compoundings is going to replace T in our calculations, right? And so we still need to know T, but oh, so jumpy today. There we go. The number of compoundings, right? This replaces T. Replaces T in our calculations. It relies on T, but it just breaks up T, which is in years, right, into the number of compoundings. Okay. So the number of compoundings, let's see here, the number of compoundings is the number of times the investment is compounded, right, until we want to cash out. The number of times an investment or loan, I guess, is compounded over the term. Okay. It's denoted by, and I just want to use the same color schemes here. It's denoted by N, a lowercase n. Now n is the time times the frequency. Okay, if you think about it, right? If I invest something for 2 years and I'm compounding, so 2 years and I'm compounding semi-annually, right? How many compoundings do I get in that term? So 2 years, twice per year makes 4, right? 2 times 2 is 4. So then I have 4 compoundings. Okay. And so n is t times f, right? Where t is the time in years still, right? So we're used to finding that. So now we're just extending it just a little bit more, right? It's the time in years. So we still need to know that. And then, and f is the compounding frequency. Oops. Okay, so how we calculate time, right, is now going to be in the number of compoundings, right? But it's built off of time in years, right? And so nothing crazy. Okay, the next thing that changes is, okay, well, this interest rate, we are always going to be given the interest rate per year, right? 3% per year, 4% per year. Okay, but because it's compounding, you don't get 3%, you get 3% broken up over the year, right? So a total of 3%. So the annual interest rate, annual interest rate, or the nominal rate. A lot of questions use the term nominal rate, so I want you to be aware of that. But it is the annual interest rate. This is the rate per year. It's going to be denoted by a lowercase r. This is the rate that the question will give you. Let's see here. The rate given in the question. Okay. What we need to do, right, is we need to break up that rate. So 4% per year, right, needs to be broken up into however many compoundings, right? And so the periodic interest rate is what does that. Man, this iPad is so touchy today. I don't know why. The periodic interest rate highlight that as well. Okay. The periodic interest rate is the interest rate, so the nominal rate broken up by the number of compoundings. The nominal rate broken up by the number of compoundings, by the number of compoundings. Which means that it's the interest rate for each compounding period. It is the interest rate for each compounding period. it's going to be denoted by I, lowercase I. You're going to calculate it. Yep. If the rate is 12% and you're compounding monthly, how much do you get each month? You get 12 divided by 12, right? And so 1% per month, which adds up to a total of 12% per year, right? But so that's how we get the formula R over F. Okay. R is the nominal rate and F is the frequency. Okay. This I is going to replace the rate, right? R in our simple interest calculations. Now that I have compound interest, okay, I need to calculate I. So it's that extra step that we introduce when we're compounding, right? That we don't necessarily see or that we don't see in simple interest. And so that's the only extension, right? Time, okay, it has to transform into the number of compoundings instead, right? So we have to do a little bit more work. The rate has to be converted to the periodic interest rate instead of just the nominal rate. And so we have to make those extensions, but then everything stays pretty well the same. Okay. So let's see here. I think I've got an example. An investment pays a nominal interest rate of 10.8% compounded quarterly. Okay. So here, let's just highlight nominal interest rate of 10.8%. This is telling me that R is 10.8 or R is 0.108, right? You're always safer to just convert it to a decimal right away. Then we're told that it's compounded quarterly. Okay. And so now this tells me that F is 4 times per year, right? And so really useful to have that table that we introduced memorized. What's the periodic interest rate? We want to know what I is. Okay. I is R over F. Oops. It's like, it's not sustainable. I then is 0.108 divided by 4. I don't think I have it here. 0.108 divided by 4 times per year, 0.027. Oops. So I is 0.027. All right, so 2.7% per quarter. Right? Or 2.7% per quarter. Right, that's what the periodic interest rate is. I have these notes that I'm going off of, but they're kind of old and I've made scribbles everywhere and I've really managed to confuse myself. I jump back and forth. So let me just get sorted here. And I think it's time. To bring in the formula sheet. But before we do, okay, so note for compound interest problems, okay, we can use the same ideas, right? So some present value grows into a larger future value, whether you've invested the present value or you have borrowed the present value, right? Whatever you've invested is going to be bigger, or whatever you borrowed, you have to pay back more. Sorry. Let me just go put it away. Hang on. Pause this. Now I have to remember what my note was. Okay, so for compound interest problems, okay. Well, let's start with how do we know we have a compound interest problem? Okay, it'll start by, not start by, but it will include some mention of compoundings. Okay, and it'll always be given. You never have to, well, I'll show you how to solve for the number of compoundings, but usually that's not how these questions are going to go. And so you will know if you have a compound interest problem. Oops, compound interest problem. If there's a mention of the number of compoundings, if it mentions the number of compoundings, when we have a compound interest problem, we have to do two things, okay? When we have a compound interest problem, we need to, first thing, and I'll put it down here, we'll need to, first thing, find the number of compoundings. So take the time given and calculate the number of compoundings. Use T to find N, the number of compoundings. N is T times F. Then use R to find I. I is R over F. Trying to use the same line. Okay. Which of course involves first having to find F, right? Figure out what F is. Okay. But that's just a general note, right? Because often when we're just starting this stuff, one of the toughest things is how do I know to use the simple interest formulas, or how do I know when I should be using the compound interest problems or formulas? And so just look out for the number of compoundings, and if it is a simple interest problem, it will say 3% simple interest. Okay. So let's see here. We're making our way through the formula sheet, right? And the compound interest section is quite large, but we've already tackled two of these. So that feels like a freebie, right? And so, and then what kind of a spoiler alert is this one is the only one you really need. And then the other three, the following three, are just derivations of the first one. Okay, and so nothing crazy. And then for annuities, we'll start in chapter 6 and 7. Okay. Oops. So here, right, you've got this formula here and this formula here. So we've already tackled those two, and just have those on there because they're just a reminder. Okay. Now, the one that I'm going to focus on today a lot is this one. Okay. And just as a heads up, we're going to be able to have changing interest rates for compound interest problems as well. And so that's what this one's doing. And then this one is for continuously compounding. So I'll just make a note of that. It's way later, but just so you have a handle on this entire section of the formula sheet. So here, this is for changing interest rates. And this is for continuously compounding. I can't remember what sections those are in, but it's at the end of chapter 5. Okay, so don't worry about them for now. So for today, this is the, I wanted the highlighter. This is the one that we want. So I'm going to copy and then I'll highlight it again. So just like we did for simple interest, what are we going to do? Well, we're going to solve for the future value. Then we're going to work on solving for the present value, right? We called it P before, but now we denote it by PV for some reason, Puerto Vallarta, right? And so, and then times 1 plus I, right? Which is from down here to the power of N. So just slight differences where N is the number of compoundings, right? And so we're just going to work through, solve for all these different components. And away we go. 5.2. Present and future values. Just to show that it's from the formula sheet here, right? We have the future value is the present value, right? Which was previously denoted by P, but if you always want to use PV, that's fine. Or P, I guess, but I've got PV everywhere. And then times 1 plus I, the periodic interest rate, to the power of N. So notice the structure of the formulas is similar, but it changes in terms of how these compoundings and how these the periodic interest rate works. Okay, and so where FV is the future value, PV is the present value, I is the periodic interest rate, and N is the number of compoundings. So remember, I is R over F, and N is the time times the frequency. Let's have a look at an example. 174. This pup sounds so upset. She's not. I think she was just rudely awakened by someone in the hallway. Okay. What's the value in 10 years of a $150 deposit at a bank, which earns, let me just go close that door. Maybe that's better. I don't know. Okay, so what's the value in 10 years of $150 deposit at a bank which earns 6.8% compounded quarterly? So remember, that's your trigger to think, okay, this is a compound interest problem, which means what? It means I need to focus on the compound interest part of my formula sheet, right? And so just kind of pay attention to the compounded, right? Tells me it's a compound interest problem. Okay. A couple of different components. 10 years is T, right? The term of the investment. So time is 10 because time is in years. So same rules apply for finding T, right? You have to convert it to years. But the the present value is 150. Now, the 6.8% is the annual rate, the nominal rate. So this is R equals 0.068. Okay. And compounded quarterly means that F is 4. Right? So again, just highlighting all the things that were given, and then it's a pretty simple timeline, but just to get in the habit of making timelines. Right, here's today, and here's 10 years from today. 10 years from today. I want to know $150 is going to grow. And it's moving forward, so it becomes a future value, right? Now, one change or a couple of changes is that, of course, I'm not going to use T anymore. I can put T equals 10 on my timeline, but I'm also going to include N, which is more important in my calculations. So N is the time times the frequency, which is 10 times 4, which means in 10 years, I would have 40 compoundings. Yeah. But this part is all you really need, because you'll have T in your calculation there. Yeah. Let's see. Right, we have R, but I actually need I for my calculation. So remember what we said, right? Is if we have a compound interest problem, I need to solve for N and I need to solve for I. Okay, so I is R over F. And I'm gonna do them across, because otherwise it's many lines for not a lot of reward. 0.068 divided by 4, which is, I have here 0.017, and hopefully that's correct. Okay. So this is the new part. Yeah. Okay. And I'll just make a note here that this is your present value is 150. Okay, let's see here. I want to find the future value is the present value times 1 plus I to the power of N, right? 1 plus I to the power of N. So I'm solving for the future value, so that's great, because it's the easiest one. The present value is 150 times 1 plus 0.017 to the power of N, which is 40. Okay. Let's see. Oh, I have it here. There. So I have 1 plus 0.017. Let me just confirm my I just a sec here. 0.068 divided by 4. Okay, good. Next line. I'm going to use that. Plus 1. Next line. So what I'm going to do here is I'm just going to show you how you should work through these formulas, right, in order to just solve it safely, okay? And so what I'm going to do is I'm going to start inside the brackets and I'm slowly going to bloom out. So my next thing is to take the previous answer and raise it to the power of 40. 40 compoundings. Okay. Take that. And then the previous answer, or maybe I'll do exactly like it's shown times the previous answer. Okay. Screenshot that and keep that. But now get rid of this. Okay. So I get the future value is $294 and rounding properly 39 cents. Nice. Okay. So the value in 10 years of $150 deposit at a bank which earns 6.8% compounded quarterly will be $294.39. All right, nice. So that's how we use this formula to solve for the future value. How about the present value? And so now let's solve for the present value. We have the future value is the present value times 1 plus I to the power of n. The present value, right? If I want to get it alone, I hold it steady, then I have to divide that whole chunk over to the left-hand side, but then I do a little switcheroo. Future value divided by 1 plus I to the power of n. Yeah. This is on your formula sheet. All right. Because it's right here. Put it here. So I'm going to show you how to derive each of these formulas, of course, but if you just want to use the formula sheet, that's totally fine. Okay. I actually prefer to have a minimalist formula sheet. So I would just prefer to have this one and then I just solve for whatever I need as I go, but here they are in case you need them. Okay. Oh, man. Hey, it won't let me change there. Okay. So, so you can solve for it. You don't have to, but we do need to know how to solve problems with it. So let's go to 175. Calculate the original principal of an investment that pays $5,437.52 at maturity over a term of 27 months at a nominal rate of 8.5% compounded quarterly. Even if you just read this yesterday, you probably would have felt like, whoa, what's going on here? Right? But so we've come a long way. We want to find calculate the original principal. So the PV is what? Of an investment that pays $5,437.52 at maturity, which makes this what? The future value, right? The future value is $5,437.52 over a term of 27 months. So T is, again, has to be in years, and we've had practice with this, right? So T is 27 over 12. 27 twelfths of a year. Okay. And at a nominal rate of 8.5%, so R, oops, I already used orange. Orangey glad. What haven't I used? Pink. The rate is 0.085. And then new color. Compounded quarterly means that the frequency is 4. Okay. So let's draw out the timeline. Look at what's going on here. Or oops, on the wrong side here. So after 27 months, let's say from today, doesn't really matter. Oops. I want to know what is the principal value that builds up to $5,437.52. Now this 5,400 is being pulled back. Okay, so I'm going to indicate that with an arrow going backwards, right? Which means what? The principal value has to be less than 5,437.52. Okay, so now let's jot down T is 27 over 12. You don't have to have it on the arrow still, but I think it helps. It's just a nice reminder. What you do need to have on your arrow is your N. N is the time times the frequency. So 27 over 12 times 4. Let's see here. Where did that little guy go? 27 divided by 12 times 4 makes 9 compoundings. Nice and clean. Okay, so 9 compoundings. Next thing I need to do is find I, right? I is R over F, which is 0.085 divided by 4. Oops. How do I? Wait. Oh. Keeps popping up with this thing here. Point. How do I? Fine. Oh. Ah. .0. Oh man. Why am I struggling so bad? I think I'm gonna have to go to the big screen here. It's crazy. Okay. 0.0885 divided by 4 is 0.02125. Nice. Okay. So now we can just use the formula that we derived for the present value, right? Remembering that you want to solve for the present value, or you can just use the original formula, rearrange it. That's fine too, right? But let's just go to the PV is the future value over 1 plus I to the power of n. The future value is 5,437.52. So what I want you to recognize is that once you have all this information here, it's really just a matter of plugging in values and using your calculator properly, right? It's nothing hard after that point. This is outlining all this stuff on your timeline. That's hard, right? But not the calculation itself. 5,437.52, 1 plus 0.02125 to the power of n, which is 9. Okay. Let's see if I can remember. Okay. So 1 plus the previous answer. Right, so I just want to show you again. So I start in the center of the brackets. The brackets just happen to be in the denominator now. Okay, but I'm still going to work through the same process. So then take that answer to the power of 9. Okay. And then 5,437.52. Oops. 37. 5437.52 divided by the previous answer. And let me see if I can. There, just screenshot. I like it when it's little. And so the present value then in money or 2 decimal places is 4499. Oh, rounding galore here. Should have known. Right, once you've rounded $4,500 even. It makes sense because this was such a choppy number that this would have started from a nice number. Okay. Not always the case, but usually. Okay, so then the initial investment was $4,500, right? And then over 27 months, it grew to $5,437.52. Nice. Okay. So that's how you calculate, just brief introductions, how to use the future value formula, how to use the present value formula. So now in the next section, we're just going to calculate the periodic interest rate and the number of compoundings. I'm going to start it on a fresh page here. 5.3, calculating the periodic interest rate which is I, and the number of compoundings or compounding periods, which is n. So we're going to start by solving for I, and then we'll solve for n, and we've got examples for both of them. Okay, so we'll start by solve for I. In the future value is the present value times 1 plus I to the power of n. So I is inside the brackets and it's being raised to the power of n. And so what do we need to do? Well, I need to do a little bit more work to shake out that power of n. How do we undo powers? We use roots, right? Nth root in this case. So the future value is divided by the present value, right? First things first, I need to divide that present value over. And so this becomes 1 plus I to the power of n. I need to take the nth root of the future value over the present value, which I'm going to do just in one line, the future value over the present value. Otherwise, it takes up too much space. Maybe I'll do that here too. Maybe not. Should show it properly first there. So I'm taking the nth root of both sides, right? Which leaves me with 1 plus I on the right-hand side. I'm solving for I, so I like to have that on the left-hand side. So in one smooth move here, I take I is the nth root of the future value over the present value, then minus 1. But again, this is on your formula sheet. If I can find the formula sheet, right? Copy. Right there. Okay. So you have it on your formula sheet, right? And so what will we need to know? How do I enter the nth root on my calculator? So there are some fancy calculators that have an nth root button where you can specify, but to calculate the nth root, on your calculator, say the future value over the present value, the nth root of that, okay, what you're going to enter is actually the future value over the present value to the power of 1 over n. Okay. So you're going to take 1 over n as the power. Okay. Okay. A little bit trickier, right? Because right, we had to do a little bit more manipulating, but we have the formula, so I'm just going to use the formula since we have it. We've already derived it. Okay. Let's do an example. 178. $15,000 was invested for 13 years until it reached a value of $30,000. Okay. If interest is compounded monthly, what was the nominal rate of interest? Okay. So a couple of things were given right away that we can highlight. The present value was 15,000. T is 13 years, so that's good. It's already in years. The future value is 30,000. It's compounded monthly, which means the frequency is 12, right? And then we want to find R. Okay. In order to find R, we need to know I, right? So solving for R will require that we first solve for I. Let me just first solve for I. Okay. Then use I equals R over F. So R is I times F. Right? Multiply that F over. Okay. Nice. So we've got kind of a game plan here. We first have to solve for I. I have a couple of things that I know already, right? And so let's just jot down a quick timeline. I would say you don't really need it, but yeah, I mean, it helps. So today, 13 years from today, 15,000 grew to 30,000. N is the time times the frequency. So 13 times 12, right? So it's quite large. Gonna try it again. 13 times 12 is 156. And I need to know what I is. Okay. Oh. Okay. The formula that we have for I is, and maybe I'll grab it from the formula sheet here. Oops. So I is the nth root, which in this case is the 156th root. Yeah. And maybe what I'll do is I'll just bump this over here. I is the 156th root of 30,000 divided by 15,000, then minus 1. So notice that the minus 1 is not inside the square root. Okay, and so let's see here. I'm going to start by simplifying inside the square root, and then I'm going to raise it to the power of 156. So let's see here. One, two, three. I think we all knew where that was going, but I want to have it in my calculator, right? So that I can go back and look at these values, make sure that they make sense. Okay, good. So this is just going to be 2, the 156th power. And so here, notice that this, the Desmos calculator does have the nth root. Okay, so you could just do this one, 156, oops, 156 over 2, right? Or let's do 2 to the power of 1 divided by 156. Notice that you get the same value, right? And so, okay, I'm not quite done, so I'm not going to do that yet. I've taken the 156th root. Now I just need to subtract 1. Answer -1. Now I can screenshot this. And now I can get rid of this there. All right, so here I use this both solve the 156th root of 2. Oh yeah, and then hey. That's the button I use to get there, right? But notice that they're all the same. So one super common thing that I see is you forget to subtract the 1, right? Because you did all this work and then you just forget to subtract the 1. But it makes a huge difference about your interest rate, right? So let me just, so I is the 156th root of 2. Maybe I'll move this down a little bit. Minus 1. So I is 0.004453137034. I encourage you to keep that value, especially for these Moodle quizzes. It's not going to be doing any rounding. And so you want to be really careful that you're not rounding until the very, very end. Okay. And so you keep all your decimal places until the end, right? Using the store function, or in Desmos, you can use just the previous answer button or store it like I showed you last day. Okay, but that wasn't the question. We wanted to solve for R. Luckily, we have I and we have F. And so now we can solve for R is I times F. So R is 0.004453137034 times the frequency, which was 12. Okay, let's see here. This times 12. So now the rate is 0.053437644441. I feel like I went cross-eyed there. 0.05343. Okay, good. Now I can round this, right? And always just make sure that it's a reasonable number, right? 5%, yeah, sounds reasonable, right? And so therefore, the nominal rate is 0.0534 or 5.34%. Nice, depending on how it wants the answer. Okay. Good. Okay. Let's do the same thing solving for n. So now we're going to solve for n. In the future value formula, I will say that in terms of working with square roots and logs and stuff, this is the time when it comes up, but I don't want you to worry so much about it from the beginning of the course, right? Because you'll have the formulas, right? So as long as you know how to use your calculator around them, then you're safe. But this is why we had to introduce, roots and logs and things like that. So the future value is the present value times 1 plus I to the power of n. And we're solving for n. Uh-oh. N is in the power. How do I shake it down? Logs, right? First thing I need to do is I need to take this present value over to the left-hand side. The future value over the present value is 1 plus I to the power of n. Right here, we need to take the natural log of both sides. When I take the natural log, the natural log of FV over PV, is the natural log of 1 plus I to the power of n. By the log laws, I'm allowed to rewrite that on the right-hand side as n times the natural logs of 1 plus I. So that's how we bring that power downstairs. Now I have n on its own, so all I have to do is divide the log of 1 plus I over to the left-hand side, but then I'm going to do a little switcheroo. And let's see here. I just want one more line here. It's going to look weird now, but when I save it as a PDF, it doesn't actually include these lines. So I'm going to count on that. So then n is the natural log of the future value over the present value divided by the natural log of 1 plus I, which again is on your formula sheet. Oh boy. I want to have it all on. I want to have it all. Maybe I should just stop talking there. I want to have it all on one page. All right, so this is on your formula sheet. All right, so all you really need to know is how to take the log, the natural log, and then you're off to the races. All right, now we can do an example. Let's see here. 179. There. I just left it alone there. In order to save for college, you want to invest $10,000 and have it grow to $15,000, period. If the rate of interest is 8% compounded semi-annually, how long will it take for this to occur? All right, so let's bump this down so I can write about it. The present value is 10,000. The future value is 15,000. The rate of interest is 8%. Okay. So the rate of interest is 8%, which means R is 0.08. Right. It'll always give you R. You have to solve for I. Compounded semi-annually. Semi-annually is twice per year, right? So F is 2. How long will it take for this to occur? Right, so T is what? In order to solve for T, I need to solve for N first. In order to solve for T, we first must solve for N. And then N is the time times the frequency, which means that T is N divided by F. So once we have N, it's going to be relatively simple to find T. Okay, let's draw out this, this timeline here. So let's say today you have $10,000, and in some unknown amount of time, it has to grow to $15,000, right? So we're forcing that. That's going to take some number of compoundings, right? Where it's compounded semi-annually. We can solve for I. I is R over F, which is 0.08 divided by 2, which is 0.04. Okay. Let's just use the formula that we have, right? I'm not going to derive it again. You can if you want to. N is the natural log of the future value over the present value divided by the natural log of 1 plus I. Now it's just a matter of plugging in the right values. Here, let's just highlight that this is the present value and this is the future value, is 15,000. The natural log of 15,000 divided by 10,000 divided by the natural log of 1 plus 0.04. Clear all. All right. First, I'm going to simplify 15,000 divided by 10,000. 15,000 divided by 10,000, 1.5. Okay, good. Then I'm going to take the natural log of that, which is in the function menu, the log of the previous answer, just to play it safe. Then I'm going to take the previous answer divided by the log, the natural log of this one. I can do in my head, right? Oops, if it didn't jump around, 1.04. Close the bracket. Okay. Good. Close this. Command there. And this looks like there. 10,000. So N is going to be 10.338 compoundings. Now, here's a note that's going to help you for the Moodle quizzes, is that Moodle is not smart enough to round this value. However, technically we can't do 10.338 compoundings, right? And 10 wouldn't get us quite to 15,000. And so we always have to round up. Okay, but that's just in kind of a real life application. And so but for your Moodle quizzes, it cannot handle the rounded values, or it's not built to handle it. So N is 10.33803,507 compoundings. Note, in the Moodle quizzes, use the unrounded value for N. In the Moodle quizzes, or in the Moodle questions, let's say, use the unrounded value for N. In real life, we can't do do 0.338 of a compounding, so we would always need to round up. Up to the nearest compounding, nearest value of n. In this case, n is 10.338, has to go to 11. Right? And I'll just clarify here, since 10 compoundings would result in less than the desired $15,000. Right, so that's the problem. Okay, but in the Moodle quizzes, questions use the unrounded value for n. Okay. Okay. So now, right, I'm just going to go ahead and use this 10.338. Okay. But if you want to try it with 11, that's totally fine too. Okay. But to match the Moodle quizzes, to match the Moodle questions, I will use n equal to 10.33803,507. Yeah. That wasn't quite done yet, right? We need to solve for n, but really what we want to know is how long is this going to take, right? So t is n divided by f. Or if you want to start at n is t times f, then 10.33803,507 is time times the frequency, which is 2. So t is going to be 10.33803,507 divided by 2. Oops. Hey, I lost it all. Okay. I'm just going to recreate the magic here. Log of 1.5 divided by the log of 1.04. That divided by 2 is 5.169 years. Usually it's fine to use a decimal, right? You could take 1.69 and multiply it by 365 for years, right? Or sorry, for days. But let's see here. Usually it just wants it as a decimal anyways. So t is 5.169 years. Okay. What if I use 11 instead? Okay. Versus properly rounding n equals to 11, right? Then what happens? Oops. N is the time times the frequency. 11 is the time times 2. So T would be 5.5 years, right? So there's quite a large difference here, right? Because here we kind of just said, oh, I'm just going to do a 0.338 of a compounding. That can't be, right? So it should be 5.5. But like I said, Moodle isn't set to round it in at the halfway point. But if it's giving you grief, then maybe try rounding. Because I remember I changed some of them to be proper, doing it properly, and then I didn't catch some of them. So just beware. All right. Okay. Good. I think that's good for today. If you have any questions, let me know. Otherwise, have a great weekend, and I will see you again on Monday. All right. Thanks, guys.